Hi everyone, welcome back. In this particular video, we're going to get started with a new topic, a new concept, in fact, which is stereochemistry. Now, stereochemistry has to do with arrangement of molecules in space, or for our purposes, we're talking about arrangement of groups around an atom in space. Okay, so it has to do with three-dimensional or spatial arrangement of molecules. So for this particular chapter, I would highly recommend getting a model kit if possible. Okay, if you have please try to get a model kit so that then you can use the model kit to visualize these molecules. Now, before we get started with the chapter itself, dig deeper into the concepts in this chapter. Let's try to connect it with what we've already seen or what we know about organic molecules. So we've talked about isomerism before, okay? And we know of one kind of isomers, which are called constitutional isomers. So we know constitutional isomers. So we know of constitutional isomers. Now, these, as we know, they have the same molecular formula, but different connectivity. And something simple, like an easy example, just to refresh everyone's memories is, if we have a 4-carbon alkane, I can draw it like this, versus that same 4-carbon alkane drawn like this. We are looking at two constitutional isomers because they have the same molecular formula. They are both C4H10. Okay, they're both C4H10, so the same molecular formula, but they have different connectivity, which makes them two isomers of each other. Now, the bulk of this chapter is going to deal with molecules which are related to each other as stereoisomers. And as I pointed out earlier in one of the videos, stereo deals with space or 3D, okay, how things are oriented or how groups are oriented in space. So stereoisomers, these have the same molecular formula and connectivity. Okay, so they have the same molecular formula and connectivity, but differ in 3D or spatial arrangement in different spatial arrangement, essentially. Okay, so that's what's different about them, how groups are oriented or how groups are arranged in 3D. And I'll draw out an example that we'll look into these later, like dig into this concept throughout this chapter, like deeper into this concept throughout this chapter. Okay, now, as an example, what we've already seen, okay, or where we've seen stereoisomers are cyclohexanes. When going over cyclohexanes, I mentioned that when you have cyclohexanes and when you have a substituent for cyclohexane, you could have a cis isomer. The two groups are both on wedge bonds. They're both pointing in the same direction, versus having the two groups pointing in opposite directions. Now, one of these groups is going behind the plane, the other one is coming above the plane. So they're pointing in opposite directions. So we can have cis and trans isomers. So cis-trans isomerism is one type of stereoisomerism. Okay, so cis-trans isomerism. That's one type of stereoisomerism. And what we will learn later is that this falls or this belongs to a broader category of stereoisomers that are called diastereomers. So we'll define later what diastereomers are, and how cis-trans isomers is basically a subcategory of diastereomers. We'll define that later. We'll define diastereomers, and then we'll see that cis-trans isomerism is basically a category of diastereomers. Now, cis-trans isomerism is not limited to cyclohexane systems. We could also talk about cis-trans isomerism in alkenes. Okay, when we have alkenes, when you have an alkene, we can imagine an alkene molecule that's like this. So we have 4 carbons, there's a double bond, and the 2 groups about that double bond are in opposite direction, versus having the 2 groups point in the same direction. Okay, so in this particular case, what we're doing is we are considering groups about that double bond. Okay, and so when we look at the double bond or the groups that are connected to the double bond, what we notice is that one of the groups is pointing up, the other group is pointing down. Whereas in the other one, both groups are pointing up, or it could be both groups pointing down, either one of those two. Okay, so since groups are pointing in opposite directions, this would be a trans isomer, and these would be the cis isomers. In fact, these two are the same molecule. Okay, these are the same, whichever one you draw. So one is trans and one is cis. So what you notice is with these molecules, each set, and just examples of what we're talking about here, notice how the molecular formula is identical. The connectivity is also identical. There's no difference in connectivity. The only difference here is 3-dimensional orientation or arrangement in space. How groups are oriented in space with respect to each other. The 2 methyl groups pointing in the same direction, methyl groups pointing in opposite direction. Methyl groups pointing in opposite direction, methyl groups pointing in the same direction. Okay, so that gives rise to stereoisomerism. So the key about stereoisomerism is that the only difference is this 3-dimensional arrangement. Okay, so those are stereoisomers, and we're going to look at various categories of stereoisomers in this chapter. Or in this portion, like as we go through this set of lectures here. Now, I also want to mention something here. Now, there are various classes of compounds that exhibit stereoisomerism, or that show stereoisomers. For the purposes of this chapter, now, we will go to alkenes later, okay? But for the purposes of this chapter, we will focus on tetrahedral carbons. And what does that mean? You're talking about carbons which are sp3 hybridized. And what that means is they have 4 groups connected to them. Okay, that will be the focus of this chapter. Like I said, cis-trans isomerism in alkenes, which deals with carbons that are sp2 hybridized, that's going to come up later. But for the focus of this chapter here, would be carbons that are sp3 hybridized. Okay, so that's like an overview of stereoisomerism. What does it mean? When do we start seeing stereoisomers? And so we'll wrap this portion up here and then dig deeper into the origin of stereochemistry for molecules. Like in molecules, what's the origin of stereochemistry in molecules in a subsequent in a subsequent lecture. Bye.